Welcome to Mrs. Z's Chemistry. In this video, we'll look at the first part of 7.6, formal charges. We can calculate the formal charge on an atom in a Lewis structure by taking the amount of valence electrons the atom is supposed to have from the periodic table and comparing that to the amount of formal electrons that the atom has. This means the amount of electrons that have been given to that atom on the Lewis structure that either you drew or that is before you. This is best shown by example. So let's first draw the Lewis structure for carbon monoxide. Carbon monoxide has a total of 10 valence electrons. If we draw our skeletal structure, it looks like this. We have a total of 10 valence electrons. Oxygen has an octet, but carbon does not. So this is where we know we need to make some double or triple bonds. Oxygen still has an octet, but carbon now only has 6 shared electrons. So let's go ahead and do this again. And here is our Lewis structure for carbon monoxide. Each one has an octet. Now we're going to assign the formal charges. So we're going to take the amount of electrons that the element is supposed to have, for carbon, that is 4, and we're going to subtract the amount of electrons that the atom has around it in this structure. So in order to count that, we're going to count each of the electrons that actually belong to carbon. Now, if you remember, these bonds each have 2 electrons. You can imagine that each of these electrons in the bond comes from one from carbon, one from oxygen. So we can say that these electrons are carbon's electrons plus the 2 lone pairs here, or the 1 lone pair, the 2 electrons. So that's a total of 5 electrons that we gave carbon right here in this structure. Of course, it still has 8 shared electrons, so the octet rule is not being violated, but we're just counting the electrons that belong to carbon, the formal electrons on carbon in this structure. So that leaves us with -1. Carbon has a -1 formal charge. I'm going to write that in a different color. Oxygen now is supposed to have 6 valence electrons, and we placed around it 1, 2, 3, 4, 5. So we have oxygen with a positive formal charge. And that is how you count the positive and formal, or the formal charges. Notice that the formal charges here must add up to equal the charge on the overall molecule. Carbon monoxide does not have a charge, it's a neutral molecule, so, well, that works. -1 and +1 equals 0. So the formal charges are not actual charges on the atoms. We're not talking about ionic compounds where one atom has lost an electron and given it to another atom that gains the electron. These are just formal charges, are a useful bookkeeping procedure. It doesn't indicate the presence of the actual charges. When we draw Lewis structures, we have to always follow the octet rule. Of course, there's exceptions, but you follow that rule first. Then, after that, we can look at this list of things that are preferable to the molecule. These are not rules that always have to be followed. There are many exceptions, but rather these are preferences. When drawing Lewis structures, you want to try to check the box on as many preferences as possible. So let's go over these preferences in the context of the molecule we just drew, carbon monoxide. Number 1, the molecule has 0 formal charges, or at least the least amount of formal charges. Now, there's no other way to draw this molecule and to give them each an octet, so we don't have any other option. This is the best we can do. So we've got a negative and a positive formal charge. Preference number 2 listed here says that if the molecule must have formal charges, the negative formal charge is usually on the more electronegative element, and the positive formal charge is usually on the less electronegative element. However, this preference cannot be followed with carbon monoxide either. Oxygen is more electronegative than carbon, yet it has to have the positive formal charge here and carbon the negative formal charge because there is no other way to draw this Lewis structure. If there was another way to draw it with giving oxygen the negative formal charge, then we would want to draw it that way. But in this case, this molecule violates, I guess, so to speak, that preference. It doesn't get to check the box on that preference of having the more electronegative element get the negative formal charge. But let's look at some more examples. So let's draw the Lewis structure for HCN. We know that carbon would prefer 4 bonds and nitrogen only 3 bonds, so we're going to put carbon in the middle. We have 1 plus 4 plus 5 valence electrons total. We're going to put carbon in the middle, and nitrogen and hydrogen on either end. We have placed 4 electrons so far. Let's place the remaining 6 electrons. 2, 4, 6. Nitrogen has an octet the way it's written here. We don't have any more electrons to give it, so in order to make carbon have an octet, we're going to remove 2 lone pairs from nitrogen and put them as a shared bonds between nitrogen and carbon. This does not take the electrons away from nitrogen. Nitrogen still has a full octet, but now carbon does as well. So now let's count the formal charges. Hydrogen is supposed to have 1 electron, and it has 1 electron on it. Therefore, hydrogen's formal charge is 0. Carbon's formal charge. Carbon is supposed to have 4 electrons, and we have placed 4 electrons around it. Remember that the bonds count as only 1 when we are counting formal charge here, because carbon owns only 1 of each of these bonds, whereas nitrogen owns these 3 bonds, or those 3 electrons, and hydrogen owns this electron. So carbon has a 0 formal charge. Nitrogen is supposed to have 5 electrons, and we have placed 5 electrons around it, these 3 and these 2 for nitrogen. So nitrogen also has 0 for a formal charge. So this has the preference of having 0 formal charges, or at least this is the least amount of formal charges here, and we don't have any formal or negative charges to place on a negative electronegative element. All right, let's do this next one. Draw the Lewis structure for ICl4. We have 5 halogens here, iodine plus 4 chlorines, each with 7. That is 35 valence electrons. This is a negative charge. That means the whole molecule has gained 1 more electron. So we need to place 36 electrons around here. We have iodine in the middle. We're going to put chlorine on all 4 sides here. We have placed 8 electrons so far, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We have 4 more electrons to place. Chlorine cannot have any more. Iodine can have the remaining 4 electrons as 2 pairs. So we have our Lewis structure here. We have to draw brackets around it because it has a negative charge. All right, let's count formal charges now. Iodine is supposed to have 7 valence electrons, and we have placed around it, let's count, 1, 2, 3, 4, 5, 6, 7, 8. Remember to count the bonds as only 1, and the lone pairs belong to iodine. So we have placed 8 electrons around iodine, therefore it has a -1 formal charge. Each of the chlorines look identical. They are supposed to have 7, and we have placed around it 1, 2, 3, 4, 5, 6, 7. So each chlorine has a formal charge of 0. The more electronegative element is in fact chlorine. Chlorine is more electronegative than iodine. So according to our second preference, chlorine should have the negative formal charge. However, we only have 1 iodine and 4 chlorines, so to make this a symmetrical molecule, it's best to put the -1 on the iodine. All right, let's do 2 more. Phosphorus has 5 valence electrons. There are 5 bromines, each with 7 electrons. So we have 40 valence electrons total. Phosphorus can have an expanded octet as it is in the 3rd row on the periodic table or lower, so it's okay to have 10 shared electrons right here. We have placed, without my lone pairs here, we have so far placed 10 electrons, so let's go ahead and place the remaining 30. We have 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Everything has an octet. Each bromine has an octet, so it's no reason to make double bonds. The phosphorus has a slightly expanded octet, but that is okay. Bromine is supposed to have 7 valence electrons, and we have placed 7 around it. 1, 2, 3, 4, 5, 6, 7. Each bromine has a formal charge of 0. Phosphorus is supposed to have 5 valence electrons. We have placed 1, 2, 3, 4, 5 valence electrons around phosphorus. Therefore, phosphorus also has a formal charge of 0. Let's draw SF6 now. Sulfur has 6 valence electrons. There are 6 fluorines, each with 7 valence electrons. We have a total of 48 valence electrons. Sulfur in the middle. And then we have here 6 fluorines around sulfur. We have placed 12 electrons so far: 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 46, 48, and I must have miscounted there. We have 48 electrons. All right, so we have sulfur is supposed to have 6 valence electrons. We have placed around sulfur 1, 2, 3, 4, 5, 6. Sulfur has a formal charge of 0. Fluorine is supposed to have 7 valence electrons. We have placed 1, 2, 3, 4, 5, 6, 7 around it. Fluorine also has a formal charge of 0. Everything has 0 formal charges in both of these structures. All right, let's do this one. ClF4 with a positive charge. Chlorine has 7 valence electrons. There are 4 fluorines. So we have 28 plus 7 more, that's 35 valence electrons. However, because of the positive charge, overall this molecule has lost an electron. We have only 34 valence electrons to place around this molecule. We have placed 8 so far: 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We have 2 more valence electrons to place. So this is a really important example of why you have to count up your total valence electrons. If you didn't do this and you just started placing electrons randomly around, you wouldn't know that you had 2 more valence electrons to place. But we do know that. Fluorine cannot have an expanded octet, so you cannot add any more. Do not add double bonds to this. And do not take lone pairs away and make double bonds. We're going to place the remaining 2 electrons as a pair on chlorine. Chlorine has an expanded octet right here, but that is okay. Chlorine is large enough to have an expanded octet. Fluorine is supposed to have 7 valence electrons. We'll do this in another color. And we have placed around fluorine 1, 2, 3, 4, 5, 6, 7. Each fluorine has a formal charge of 0. On the chlorine is supposed to have 7 valence electrons. We have placed 1, 2, 3, 4, 5, 6 around it. Chlorine has a positive formal 1 charge. Positive 1 formal charge. So we can put brackets around this whole thing with a positive charge on the outside, just because the molecule has a charge, and chlorine is the one that has the positive formal charge. This actually does follow the preference that says that if you're going to have formal charges, the more electronegative element will have the negative one, and the less electronegative element would have the positive formal charge. Speaking of preferences, let's review this list of preferences and add a couple to the list. So again, number 1, the molecule has 0 formal charges, or at the very least, the least amount of formal charges possible. Choose a structure that has the least amount of formal charges. Number 2, if the molecule must have formal charges, the negative formal charge goes on the more electronegative element. And that's, of course, again, usually. These are just preferences. Number 3, the less electronegative element is usually in the middle. The less electronegative element usually prefers to make more bonds, and so they can be the central atom much easier than more electronegative elements. And the last preference here, most, if not all, of the atoms in the molecule should have their preferred number of bonds. Let's look at a periodic table and review the bond preferences, or the bond number preferences. So looking at this periodic table here, let's look at fluorine. The fluorine column. The fluorine column, the halogens, they prefer, or they only need 1 more valence electron in order to have the nearest noble gas electron configuration. So because the halogens want to add only 1 more electron, they prefer to make only 1 bond. And then they would have their 3 lone pairs. The oxygen column, oxygen, sulfur, and selenium. Let's go ahead and put our little staircase here, because these are really only applying to elements that are above the staircase, because we only care about these nonmetals in the covalent bonds. Our oxygen column here, they would like to gain 2 electrons in order to have the same electrons as the nearest noble gas, so they would usually prefer to make 2 bonds. Nitrogen column would prefer to make 3 bonds because they need 3 valence electrons. The carbon and silicon column here would prefer to make 4 bonds because they need 4 electrons. Now, for boron, this is where the little trend kind of breaks down for the number of bond preferences. Boron only has 3 valence electrons, and it needs 5 more in order to fill its octet. However, that's a lot of electrons for a little boron to attract because there's only 5 protons in boron. So boron usually just makes 1 bond with each of its 3 valence electrons, and so it usually only makes 3 bonds, and it actually often doesn't have a full octet. And then beryllium, sometimes there are covalent bonds made with beryllium here. Beryllium only has 2 valence electrons, so it usually only makes 2 bonds, and that's really just for beryllium. For hydrogen, of course, because it only has 1 valence electron, it prefers only 1 bond. Actually, that's more of a rule. Hydrogen will never make more than 1 bond. All right, so let's go ahead. Keeping all of these preferences in mind, let's draw this. Let's see if we can figure out the best Lewis structure for these given formal charges as well as the preferences. Pause to see if you can work this out. All right, so we're going to choose the less electronegative element from here. Looking at a periodic table, sulfur is further to the right, but it is lower on the periodic table, so it's difficult to tell between carbon and sulfur which one is more electronegative. And in fact, if you were to look at a periodic table with the electronegativity numbers, carbon and sulfur have the same electronegative number. They're both 2.5. So you could either put carbon or sulfur in the middle. Nitrogen is more electronegative, so we're not going to put nitrogen in the middle. Between carbon and sulfur, though, carbon prefers 4 bonds, sulfur prefers 2. So it'd be better to put carbon in the middle to make more bonds. So we're going to draw this structure. Oops, we're going to put carbon in the middle. We could draw it with, let's count up our total number of electrons. 4 plus 5 plus 6, then plus 1 more. So we have 16 valence electrons we need to place around this structure. 2, 4, 6, 8, 10, 12, 14. Oops, that's too many. Let's go like this. 2, 4, 6, 8. 10, 12, 14, 16. So there, everything has an octet. We've got 16 valence electrons. We'll count formal charges in a moment. Let's do another one. Let's put nitrogen in here, but let's do a triple bond, carbon and a single bond. There's also 16 valence electrons. Everything has an octet. And then this other option, let's put the triple bond on the other side. All right, let's count up formal charges here. So we're going to look at nitrogen is supposed to have 5 valence electrons, and we have placed around it 1, 2, 3, 4, 5, 6, 7. That means nitrogen has a formal charge of -2. Carbon is supposed to have 4. We have placed 4 valence electrons around it. This gives carbon a 0 formal charge. Sulfur is supposed to have 6 valence electrons. We have placed around it 1, 2, 3, 4, 5. That gives sulfur a +1 formal charge. That's kind of a lot of formal charges here. -2 and a +1. It does equal to the -1, which is great, what it needs to. But let's move on over here. Nitrogen is supposed to have 5 valence electrons, and we have placed 5 around it. 1, 2, 3, 4, 5. Carbon is supposed to have 4 valence electrons. We have placed 4 around it. Sulfur is supposed to have 6 valence electrons. We have placed around it 1, 2, 3, 4, 5, 6, 7. So we have a -1 on the sulfur. Much better. 2 of the atoms have 0 formal charges, and sulfur has a -1. Let's see what this one has. Nitrogen is supposed to have 5 valence electrons. We have placed around it 1, 2, 3, 4, 5, 6. Nitrogen has a -1 formal charge. Carbon is 0 because we have 4 minus 4 here. And then sulfur has supposed to be 6 valence electrons. We have placed around it 1, 2, 3, 4, 5, 6. All right, so between these two that we just counted, we're going to discount this last one over here because it has a lot of formal charges. So we're going to look at these two right here. Which one is more electronegative? Well, the nitrogen is more electronegative. So that this structure here follows that preference. So if you can draw it like we can here with the -1 formal charge on the more electronegative element, then this would be our preferred structure. All right, let's do this again. With this last example, go ahead and pause and see if you can work this problem out. All right, so let's go ahead and count up our valence electrons. We have 5 plus 5 for the nitrogens, plus 6 more for oxygen. We have a total of 16. Now, between nitrogen and oxygen, the more electronegative element is oxygen, so we're not going to put oxygen in the middle. We're going to put nitrogen in the middle. I know this might seem a little bit weird considering it would be more symmetrical putting oxygen in the middle. We're going to follow this preference first, though. So we have a total of 2, 4, 6, 8, 10, 12, 14, 16. Let's just place a bunch of electrons around. All right, so we can see that oxygen has an octet, but the nitrogens do not. So let's go ahead and share. Oops. We're going to take off a lone pair from oxygen, make a double bond, and then let's go ahead and do it again right here, actually, and share there. So we have oxygen has 2, 4, 6, 8. The middle nitrogen has 8, and the end nitrogen also has 8. So there's one structure. Let's try it again with maybe a triple bond. So far we have placed 2, 4, 6, 8, 10, 12, 14, 16. So there's another way to draw it. And then let's draw it again. Here, let's put the triple bond on this side. All right, so we have 2, 4, 6, 8 for oxygen, 8 for the middle nitrogen, 8 for the end nitrogen. Let's go ahead and do formal charges, count up formal charges here. The left-hand nitrogen is supposed to have 5 valence electrons. We have placed around it 1, 2, 3, 4, 5, 6. This equals -1 for this nitrogen. The middle nitrogen has a 5 minus 4. It has a +1. The end oxygen has 0. Okay, so we've got a -1 and a +1. It overall equals to 0 because this molecule is neutral, so that's fantastic. Let's see if we can get even less formal charges, if possible. All right, so we have 1, 2, 3, 4, 5, 6, 7 for around this nitrogen, so that's 5 minus 7. Uh-oh, that's -2. That's even more. This is also a +1, and then we have a +1 as well. So again, it neutrals out to 0 for the formal charges, but we've got even more formal charges. Let's check on this one. We have 5 minus 5 is 0 for this one. We have a +1 here because that's 5 minus 4. And then the end oxygen is supposed to have 6, and we've placed around it 1, 2, 3, 4, 5, 6, 7. That equals -1. All right, so it looks like we will ignore this middle one here because that has a lot of formal charges. So between the outer two structures, we've got a -1 on either the nitrogen or the oxygen. Because oxygen is more electronegative, we're going to choose this structure as our dominant structure. This is probably the most preferred and most accurate structure here that we have written.